Hi friends, and welcome to my channel. Today I'm going to show you how to solve this problem using separation of variables by considering this boundary condition. So we have boundary condition 1 and boundary condition 2, and here is our governing equation. Okay, so to solve this, first of all we need to note that we're going to replace our theta with x times y. And if we do so, we'll realize that the squared theta over the x squared is simply going to be x double prime y, okay, and this squared theta dy squared is x of x, then y double prime, okay. And if we put this back to rewrite the governing equation, we're going to have that x double prime y plus x y double prime equals to 0, okay. And we could just replace wherever we have our x, we could just call it x, and our y of y, we could just call it y, just to avoid unnecessary repetition. So if that's the case, let me write this. It's just going to be x double prime y plus x y double prime equals to 0. We're going to divide both sides by x y, okay, x y, okay, and this is simply going to end up as x double prime all over x plus y double prime all over y, and this is simply 0. Next, we're going to move this to the right hand side, so we're going to have that x double prime over x is equals to negative y double prime over y, and because they're equal, we can easily see that this is equals to negative lambda squared. So next we're going to do is we're going to write an equation for this equals to this, and then this being equals to this as well. So if we do so, we're going to have the first one is going to be x double prime over x is equals to negative lambda squared, and y double prime over y, negative y double prime over y, will be negative lambda squared. And if we rewrite this, we're going to have that x double prime plus lambda squared x, this equals to 0, and y double prime minus lambda squared y, this is equals to 0. And the solution to this is simply x of x is equals to c1 is a constant sine lambda x plus c2 another constant cosine lambda x. And for this we have that y of y is going to be c3 hyperbolic sine of lambda x plus, we can write it under here, c4 hyperbolic cosine of lambda, this is lambda y, this is lambda y, please, okay. I'm sorry, I'm just going to wipe it out. This is lambda y. Alright, so these are the solutions. And if you have any doubt about this, I'm just going to prove this, that this is actually correct, just one of them. So what is x double prime? This is simply lambda squared, negative lambda squared, c1 sine lambda x, okay, minus lambda squared c2 cosine lambda x. And what is lambda squared x, which is this here? This is simply going to be lambda squared c1 sine lambda x plus lambda squared c2 cosine lambda x. And when you combine these two, this will take away this take away, all we have left is 0. So this solution is actually correct, and you can take your time to verify this. You're going to get the same thing. Alright, so let me wipe this up and we'll get back to the problem. So moving forward, here we have the x's. I'm going to apply boundary condition 1 that deals with just x's, and boundary condition 2 that deals with y conditions. So here we have that theta is 0 at x is 0, and here is 0 at y is equals to 0. So applying boundary condition 1 here, which states that x at x is equals to 0 is equals to 0. Here x represents our theta, since theta is xy and there's no y at all. Okay, so let's put that in this solution. We have this would be 0 is equals to c1 sine theta. X is 0, so this would be sine 0 plus c2 cosine 0, and sine 0 is 0 and cosine 0 is 1. So we have that 0 is simply equals to, this is 0, c2 times 1, so which implies that c2 is equals to 0. And if that's the case, we're going to put that back into this our solution, that c2 is 0. And if that is the case, we have that x of x is now just going to be c1 sine lambda x. This c2, this term here goes to 0 because c2 is 0. Okay, and let's go to the next one. Let me draw this line here. So to apply the boundary condition here, we have that y at y equals to 0 is equals to 0. Okay, so that simply means that this solution is going to be 0 is equals to, I'm talking about the solution here, c3 sine 0. So c3 hyperbolic sine of 0, then plus c4 hyperbolic cosine of 0, and this we know is 0 and this is 1, so which implies that 0 here is equals to c4 times 1, which is c4, and this implies that c4 is 0. Then we're going to apply that back into the solution. That means this whole term here is going to become 0 because c4 is 0. So we have that our y of y is simply c3 hyperbolic sine of lambda y. So therefore, now we apply the two boundary conditions, and we recall that theta is xx dot yy. Okay, so which means that theta is x of x dot y of y, and here we have our x, and here we have our y, so which implies that theta is simply c1 sine lambda x times c3 hyperbolic sine of lambda y. But since this is a constant and there's a constant, we can just call it c1 or just c. So this is simply equals to c sine lambda x hyperbolic sine of lambda y. And that is the solution to our problem. We found our theta for this problem using these boundary conditions. So this is the first step. In the next video, I'm going to do more problems using separation of variables to solve equations of this nature to find our theta using separation of variables. Thank you very much, guys. If you have any question, please do drop it in the comment box, give us a thumbs up and a like, and see you in the next video. Thanks.